So, somewhere in between 0 and pi, the first derivative has to equal the average rate of change. So we'll take the derivative. We'll get 2 sine, take back, root of sine is cosine. 2 cosine of x plus 2 cosine of 2x. All right, that's what we get if we take the derivative. And then that's going to equal the average rate of change, which should be g of 0, take it back, g of pi minus g of 0. Actually, I guess I could have kept g of 0 as long as I kept the denominator the same. G of pi minus g of 0 over pi minus 0. So let's see here. So I'll put sine and put pi in there, we're getting 0, huh? Sine of pi is 0. Minus sine of 0 is 0. So it's going to equal 0. So the average rate of change is 0. That means if we go from where this graph started to where it stops, it could change direction. It's going to wind up there, or it could just do this or that. And see over here I've got 2 cosine of x plus 2. How are we going to deal with this cosine of 2x? Double angle identity? Anybody remember the double angle identity for cosine of 2x? That's sine of 2x.
Cosine squared minus sine squared.
Cosine squared minus sine squared. Then we're going to run into even more hassles here. Because then we're going to get 2 cosine squared minus 2 times sine squared. I don't want that sine squared, so why couldn't I replace the sine squared? 1 minus cosine squared. So now we got 2 cosine of x plus 2 cosine squared of x minus 2 plus, well, I was almost hoping those would cancel out, plus 2 cosine squared of x. So we got 4, 2 cosine of x minus 2. So I guess I could go through and divide everything by 2 and get smaller numbers. Get 2 cosine squared plus cosine minus 1. So we could factor this just like it was 2x squared plus x minus 1. I know it's got to be a 2 cosine times something. And then the other thing's got to start out with cosine. That's the only way to get 2 cosine squared. And we want to wind up with negative 1. So one of these has to be a positive 1 and negative 1. But we want the middle term to be positive. So negative 2 cosine x minus 1 and cosine x plus 1. That would get us here a 2 cosine minus cosine like that. So then we want to know where each part is 0. So 2 cosine x minus 1, for that to equal 0, cosine would have to equal 1/2. And for cosine x plus 1 to equal 0, cosine would have to equal negative 1. So we want all the values in between 0 and pi. Now, remember that advanced students take calculus. Here's 0, here's pi. So cosine would equal 1/2 in the first quadrant and the fourth quadrant. We don't need to worry about the fourth quadrant. That's bigger than pi. 1/2 is 60 degrees, or pi over 3. If you're positive. Oh, you're trying. Yeah, I just say we could scroll back. You know, if you're taking a test, once you write that triangle once, you've always got it. How about where's cosine equal negative 1?
Well, that value, because it's outside of it.
Yeah, well, that's actually one of the endpoints, huh? Pi is one of the endpoints, so we don't count that one, so we just take the pi over 3. So
The whole process pretty similar to the
I think.
Rolle's theorem.
Yeah.
The difference is that you just don't test the endpoints.
Well, in Rolle's theorem, we never tested endpoints either. It's streama, the maximums and minimums we did. Rolle's theorem, we were just, if the f of a equaled f of b, the function was continuous and differentiable, then somewhere the first derivative had to equal 0. Which I'm going to graph this from 0 to pi. Do zoom fit just to look at this.
But here we're still setting the derivative equal to 0.
Well, in this case, we set the derivative equal to the average rate of change. The average rate of change turned out to be 0. Yeah. See, when we look at this graph, it turned out to be 0. And maybe I could have shown on that last one why we don't include the endpoint. Like, this right here must be at pi over 3. If I draw a line from here to here, here's our secant line. It's got a slope of 0. Here's our tangent line. It's got a slope of 0. According to what we just figured out here at pi, there's also one, but since pi is the endpoint, I could draw a tangent line like that, like that, like that, like that, like that. So if we stop there, we don't know what's after it.